Sustainability is key for built environment projects, but retrofitting terraces such as these have challenges of their own. The Energy House is a typical 2-up, 2-down terrace which was originally built in 1910. In 2010 it was removed brick by brick and rebuilt in a laboratory located at Salford University.
Yeah, the whole kind of idea around the house in the lab is to build a structure, a building. In our case it's a 1910 house in a controlled environment, and it's the only one in Europe, and it means we can do lots of types of experiments you wouldn't necessarily normally be able to do in the outside environment. Well, this house in the laboratory is actually a traditional Salford house, which was actually outside in the real environment about 1.5 years ago, and we've taken it down brick by brick and basically brought it back to Salford and built it in this chamber. And we follow traditional building methods, so we've got a lath and plaster ceiling, no insulation at all, lime mortar, and as original as we can make it. So you can see that the windows are also the normal sash single glazed windows, as you would have for this type of period, which is about 1910. And we've built this particular type of house because it's the hardest to treat, and it represents about 20–25% of the types of houses we have out there in the environment. It's a single wall, so there's no cavity, so this causes some issues in terms of how you make this a more energy efficient house in terms of insulation. And if we can treat this house, we can transfer this knowledge to perhaps more modern type buildings and structures. I mean, there were definitely challenges to build this structure. Everything down from, you know, a lime mortar, and particularly a lath and plaster ceiling. You know, in a modern building, it normally takes 2 or 3 days to put a ceiling up and skim a ceiling. Here it took us 8 weeks for the actual ceiling to dry, and actually finding somebody with those skills to put a lath and plaster ceiling up, which obviously you wouldn't do in a modern house, was quite challenging. So we're trying to find people with those skills from 30, 40, 50 years ago. So that was quite a big challenge, and building methods have changed. So we had to take those into account, because we are trying to recreate a 1910 house, not a 1990 or 2000 house. So yes, there were some challenges. There's a whole range of experiments we can do. One of the key experiments we're doing is around new materials. And you can test these in a small laboratory. You can test small parts of the materials, but when you actually want to see how they perform in a real environment, in a real house, particularly things like insulation materials, ideally you want to be able to control the temperature inside the house and have a cold environment outside. Now, in the middle of summer, if you're outside, you can't do this kind of experiment, because the temperature difference is quite constant, and it's quite similar. In an ideal world, you'd have 10 or even 20 degrees difference between the inside and the outside of the house, which means we can do that kind of experiment here, and therefore we can rapid test things. So as you can see, we have a thermal imaging of the camera, and you can't really take any meaningful thermal imaging of buildings, any building really, in the middle of summertime when the heating's off. You have to wait to the winter time, which means that it's kind of quite a short season when you can do testing. So there's lots of things we can do in our house which you can't necessarily do in the real environment. Well, the overall objective is to reduce our carbon footprint of buildings, particularly domestic buildings. And this is very important. You know, that they're very complicated buildings. You have people in these buildings. They're very different types of buildings, and we need to reduce the amount of energy we use. And we're looking at more sophisticated methods of actually reducing people's energy use. So we're looking very much at the domestic market for domestic buildings, and there's 26 million houses, so it's a huge problem, and it really is an old building problem. If you were to look at new build, I mean, last year we only built about 100,000 new buildings. We have 26 million old buildings. So the real challenge is how to make older buildings more energy efficient. And that would be through a various combination of different methods. And what we're trying to do is match people with building type and then technology. It's not just a technology problem. People use energy. Buildings don't use any energy. It's people who use energy. So it's understanding how people use energy, who uses energy, and therefore what the best technical solutions are for those types of energy use and profiles, and to match that with the buildings. We know a lot about buildings, but we know very little about how people actually use energy and what energy is wasted. So that's a very important area we're trying to develop here at Salford. Reducing the carbon footprint of buildings is not just a UK problem. Of course, it's an international problem. So one of the key areas we're working with and key countries is actually India. India has a population of 1.2 billion pounds. It's one of the fastest growing economies in the world, and it's important that we help bring some of the knowledge we have and also exchange this knowledge, some of the knowledge which is in India, to reduce the carbon footprint of our whole environment, not necessarily just UK or even Salford. It's an international problem, it's not just a UK problem. One of the key partners we're working with is the Indian Green Council, who are a big organisation in India, one of the largest, has 94,000 businesses associated with it, all working around reducing the carbon footprint of India. India has a population of 1.2 billion people. This is a global problem. India has a cooling problem, the UK has a heating problem, but it's still a very similar type problem. It's how we heat or cool our buildings very efficiently and how we keep heat in or keep heat out.